Module 4, Lecture A, Material Balances. By the end of this lecture, you will be able to represent process streams and component flow rates in Python, compute material balances for mixers, splitters, and reactors, and check balance closure and identify inconsistent input data. Stream models, component flow rates. A process stream is a moving mixture of materials, and its total flow rate does not fully describe it. To understand and model the stream, we need the flow rate of each component, such as methane and carbon dioxide in natural gas, or water and sugar in a liquid feed. These component flow values give Python a clear, structured description of what is in the stream and how much is moving. When describing a process stream, each component should be tied to its flow rate and unit. Treating components as separate, named parts of the stream makes the data easier to use in Python calculations, such as combining streams or checking available reactants. It also helps engineers inspect the stream quickly, confirm that all needed components are included, and spot unusual values. Careful tracking of component flow rates helps prevent material balance errors before calculations begin. Mass flow rates and molar flow rates must be kept distinct because they cannot be combined directly. Even small impurities can matter for product quality, downstream processing, or environmental compliance. Consistent flow rate representation makes Python useful for organizing process data and supporting accurate material balance analysis. Python code, component flow rates. Stream dictionaries track the flow rates of each component, keep units consistent throughout calculations, and use small checks to catch missing components early. A feed stream dictionary stores the mass flow rates of each component in a stream, such as water, ethanol, or salt. Each component name is linked to its flow rate in kilograms per hour, making the stream easy to manage and use in later calculations. The code defines kilograms per hour as the flow rate unit and uses it consistently in the calculations. This keeps the component flow rates clear and easier to interpret. Find the total feed flow by adding the flow values for all components in the feed stream. This combined flow rate is needed for later calculations, such as mass fractions or checking whether any components are missing. We create a mass fractions dictionary to describe the feed stream composition. For each component, its flow rate is divided by the total flow to find its share of the stream. The component name is stored with this fraction, showing how much each component contributes to the total mass. The expected components set lists the stream components the model should contain: water, ethanol, and salt. It is used to check that the feed stream includes everything needed, helping ensure the model is complete and accurate. This step checks whether the feed stream is missing any required components. It compares the expected components, water, ethanol, and salt, with the components actually present in the feed stream. Any difference identifies missing items, helping ensure the calculations include everything needed. The code prints a heading that introduces the feed stream component flow rates. This organizes the output and prepares the reader for the following details on each component's flow rate and mass fraction. The process reviews each component in the feed stream, using its name and flow rate to find its mass fraction. It then reports a concise summary showing the component name, rounded flow rate with units, and rounded mass fraction. This gives a clear view of how each component contributes to the total flow. The code reports the total flow rate of the feed stream components. It formats the value to 1 decimal place and labels it in kilograms per hour, making the result clear and easy to read. The code verifies that the stream model contains every expected component. It compares the expected components with those present in the feed stream, reports any missing items in sorted order, and otherwise confirms that the model is complete. The script summarizes a feed stream made of water, ethanol, and salt by calculating the total mass flow and each component's mass fraction. It then displays each component's flow rate and fraction, along with the overall flow. Finally, it checks the stream against the expected components and reports whether anything is missing, helping verify that the stream data is complete and consistent. Stream components. A process stream is a mixture of chemical components, each with its own identity and amount. In modeling, the first task is to define which components are present and name them consistently. This component model determines what material balances can track and helps keep flow rates and compositions organized, readable, and traceable in Python-based calculations. Choosing components for a process stream requires both chemical understanding and practical judgment. Some species must be modeled separately when their properties matter, while similar substances can sometimes be grouped into a pseudo-component. The right level of detail depends on the purpose of the calculation, from simple mixtures to more complex reactions. A clear stream representation helps others judge whether the model is suitable for the engineering task. In process calculations, component names must be consistent, because the computer treats each name as a separate identifier. Before doing material balances, standardize names and make sure all streams, such as fresh feeds and recycle streams, use the same component set. This prevents missing materials, double counting, and other errors in Python-based calculations. Python code, stream components. Use consistent names for stream components so different streams can be compared and aligned. Store each component's flow rate in a dictionary, and use shared lists to keep the component order consistent across streams. We first define the standard process components: water, sucrose, ethanol, and carbon dioxide. These are the substances tracked in each stream, giving all streams a consistent set of component names. This shared reference supports accurate alignment, comparison, calculations, and analysis. 2 stream dictionaries are created to store component flow rates. Feed A contains water at 90 and sucrose at 10, while Feed B contains water at 40 and ethanol at 5. This structure makes it easy to organize and work with the components in each stream. The align stream function standardizes a stream dictionary to match a given component list. It creates a new dictionary that keeps existing flow rates and assigns 0 to any missing components, so all streams use the same component set. Each feed is aligned to the same standard component list by matching every component to its flow rate and using 0 when a component is missing. This is done for both Feed A and Feed B, so they share a consistent representation. With both feeds standardized, balance calculations become easier and more accurate. A new dictionary is used to store the mix stream by combining matching components from 2 aligned streams. For each component, its flow rate from the first stream is added to its flow rate from the second stream. The result gives the total flow rate for each component in the combined mixture. Combine the component names from Feed A and Feed B to find all unique components in the streams. Then compare that combined set with the standard component list. Any remaining names are components found in the feeds that are not recognized as standard, helping identify unexpected or unknown entries. The process first shows the standard component list, including water, sucrose, ethanol, and carbon dioxide, to establish a common reference. Feed A and feed B are then aligned to this list so their components can be compared consistently. The mix stream combines matching component flow rates from both feeds, and any component names not found in the standard list are reported in sorted order to reveal possible discrepancies. This script standardizes two chemical feed streams against a fixed component list: water, sucrose, ethanol, and carbon dioxide. It fills in missing components with zero flow, combines the streams by adding each component's flow rate, and reports the final mix stream. It also flags any components in the original feeds that are not part of the standard list. Molar flow rates. Molar flow rate describes how many moles of material pass through a boundary over time, making it especially useful in chemical process analysis. Unlike mass flow rate, it reflects the amount of substance, which matters for reactions and composition. Using molar flow rates helps track each component consistently across feeds, products, and other process streams. In stream models, molar flow rates are tracked for each chemical species rather than only as a total. This shows both the stream's overall flow and its composition, which is important for processes such as air separation and natural gas processing. A good stream model makes it easy to access component flows, calculate the total, compare streams, and identify missing or incorrect values. Molar flow rates must be handled with consistent units and clear physical meaning. Values such as moles per minute, kilomoles per hour, or millimoles per minute cannot be combined directly without conversion. In material balance calculations and process software, consistent component molar flow rates are essential for accurate streams through mixers, splitters, and reactors. Python code. Molar flow rates. Represent each stream component by its molar flow rate, using dictionaries to keep component names clear and readable. From these component flows, you can directly determine the total flow and the corresponding fractions. A stream flows dictionary stores the molar flow rates of each component in a stream. Component names such as nitrogen, oxygen, and carbon dioxide are used to look up their flow rates in kilomoles per hour. This makes the data easier to read, access, and update in the code. The code first checks that all component molar flow rates in the stream are non-negative. If any flow rate is below zero, it raises an error. This validation helps ensure the stream data is physically meaningful and safe to use in later calculations. The total molar flow rate is found by adding the molar flows of all components in the stream. This single total is needed to calculate values like mole fractions and to support later analysis or validation. The code first checks that the total molar flow is positive before calculating composition. If the value is 0 or negative, it raises an error instead of continuing. This prevents invalid division and ensures mole fraction results are meaningful. Molar flow rates are converted to mole fractions by dividing each component's flow rate by the total molar flow rate. This creates a new set of values that shows each component's proportion in the stream, making the stream composition easier to interpret. The code checks whether the stream composition is properly normalized by adding all mole fractions, which should total 1. It then finds the closure error as the absolute difference from 1, showing how closely the composition satisfies this accuracy check. The code first states that the stream flow rates are based on kilomoles per hour. It then reports the total molar flow to 2 decimal places, giving a concise view of the stream's overall flow rate and scale. The code goes through each stream component, gets its flow rate, and matches it with its mole fraction. It then prints a clear summary showing the component name, flow rate in kilomoles per hour, and mole fraction rounded to 3 decimal places. This helps show how each component contributes to the overall stream. The code checks whether the mole fractions add up to 1 by measuring the absolute difference between their sum and 1. It prints this closure error in scientific notation, helping confirm that the composition calculations are accurate. The script summarizes a gas stream made of nitrogen, oxygen, and carbon dioxide. It checks that all molar flow rates are non-negative, verifies the total flow is positive, then converts each component flow into a mole fraction. It also checks that the mole fractions sum close to 1 and reports any closure error, along with the total flow and component composition. Unit operation balances. Mixer balances. A mixer combines several inlet streams into one outlet stream. In process calculations, the main rule is conservation of mass. The total amount of material and the amount of each chemical component entering the mixer must leave it if nothing is lost or changed inside. The outlet flow rate and composition are therefore determined by the flow rates and compositions of the inlet streams. In a mixer balance, track both the total flow and the flow of each component. The mixed outlet flow equals the combined inlet flows, and each component leaves in the total amount contributed by all inlets. For concentrations, the outlet is a flow-weighted mixture, not a simple average, unless the inlet flow rates are equal. Accurate calculations require considering both how much stream enters and what each stream contains. Mixer balances help check whether process data are physically consistent. Inlet and outlet flows should agree within expected limits, and outlet compositions should fall within plausible ranges. If they do not, the data may suggest leaks, missing streams, or another unaccounted process. These checks are important in applications such as fuel blending and pharmaceutical formulation because they enforce material conservation and support sound engineering judgment. Python code, mixer balances. Mixer balances are used to combine incoming process streams. Tracking component flows helps determine compositions more easily, while closure checks help identify inconsistent data. Two inlet streams are defined as component flow dictionaries. The first contains 90 kilograms per hour of water and 10 kilograms per hour of salt, while the second contains 50 kilograms per hour of water and no salt. This structure makes it easy to track and adjust each component's flow rate. First, collect all inlet stream dictionaries into one list so they can be processed together. Then identify every unique component by combining the component names from all streams into a set. Sorting these components gives a consistent order for later calculations and comparisons. Create an outlet stream with all component flows set to 0. Then add the matching component flows from each inlet stream. If an inlet stream lacks a component, treat its flow as 0. This produces the total flow for each component, which can then be used to calculate overall flow and composition. To check the mixer balance, add the flow rates of all components leaving the outlet to get the total outlet flow. Then add the component flows in each inlet stream and combine those totals to get the total inlet flow. Comparing these two totals helps confirm that the mixer flows are consistent. An empty dictionary is used to store the mass fraction of each component in the outlet stream. For each component, its flow rate is divided by the total outlet flow to find its share of the mixture. These values describe the outlet stream composition. Define the measured outlet by its water and salt components. Then add them to get the total measured outlet flow. Compare this value with the previously calculated total inlet flow by finding the difference between them. This closure error shows how well the measured and calculated flows agree and highlights any discrepancy in the flow balance. The output reports the calculated outlet component flows and their total in kilograms per hour, then shows the outlet salt mass fraction rounded to 4 decimal places. It also compares the measured total outlet flow with the inlet flow by calculating a closure error, rounded to 3 decimal places. Finally, it checks whether this error is within 1 kilogram per hour and reports a true or false result to indicate whether the mass balance is consistent within the chosen tolerance. This script models a mixer with 2 inlet streams containing water and salt. It adds the component flow rates from both inlets to find the outlet composition, then calculates the total outlet flow and the mass fractions. It compares the calculated total flow with a measured value to find the closure error. If the error is within 1 kilogram per hour, the material balance is considered consistent. Splitter balances. A split divides one input stream into several output streams without changing the material or its composition. It does not react materials or separate components unless a special split is specified. For a well-mixed inlet, each outlet has the same composition as the original stream, and only the flow amount changes according to the chosen split fraction or flow rate. In a simple splitter, total flow and component flows must be treated consistently. Because the outlet streams have the same composition as the well-mixed feed, any outlet that receives a fixed fraction of the total flow also receives that same fraction of every component. This applies to common cases such as piping tees and purge streams, where a purge removes part of a recycle stream without changing its composition. Splitter balances check whether process data are consistent by confirming that total and component flows leaving a splitter match what enters, since an ideal splitter does not store material. If the outlets show more material than the inlet can supply, the data or assumptions may be wrong. Common causes include measurement error, poor sampling, leaks, or unintended separation such as solids settling before the split. Good engineering judgment means verifying that the unit is behaving like an ideal splitter and that the input data are reliable. Python code. Splitter balances. A splitter divides a stream into outlet streams without changing the species present. Each component flow is split in the same proportions as the total stream. Material balance checks can be used to spot inconsistent splitter data. A well-mixed feed stream is represented with a simple dictionary containing the component flow rates: water at 80 kilograms per hour and ethanol at 20 kilograms per hour. This structure makes it easy to access and use each component flow in later calculations. The feed is split between 2 outlet streams. 30% goes to the cooling stream, and 70% goes to the washing stream. These split fractions divide the total flow while preserving the overall system balance. To verify that the feed stream is fully divided, add all the split fractions together. If their total is 1, the fractions account for the entire feed across the outlets. For each outlet stream, we create a component flow breakdown based on the feed stream. Each component's feed flow is multiplied by that outlet's split fraction, so the outlet flows stay proportional to the original feed. Repeating this for all outlets produces a nested structure with the component flows for each outlet. To find the total feed flow, add the flow rates of all components in the feed. This combined value is used to compare the feed with the outlet streams and check that the mass balance is satisfied. To find the total outlet flow, Add the component flows within each outlet stream, then add those stream totals together. This gives the complete amount of material leaving the system through all outlet paths. Balance residuals show the imbalance for each feed component by comparing what enters with what leaves. For each component, subtract the total amount in all outlet streams from the original feed amount. The result is the residual, which indicates whether input and output flows are balanced. An intentional error is introduced by adding 5 to the calculated water flow at the washing outlet. This creates a mismatch between the measured and expected values, helping demonstrate how discrepancies can be detected and examined during material balance checks. We calculate the washing outlet flow inconsistency by comparing the measured water flow with the ideal flow. The difference shows how much the actual measurement deviates from what is expected, helping check the accuracy of the splitter balance calculation. This check summarizes a material balance around the feed split. It totals the feed flow, verifies that the split fractions add to 1, and then totals the cooling and washing outlet flows. The combined outlet flow is compared with the feed to confirm overall balance, while water and ethanol are checked component by component using residuals. Any mismatch in the measured washing water flow is then identified by comparing it with the ideal calculated value. This script simulates splitting a water and ethanol feed into cooling and washing outlets using specified fractions. It checks that the fractions add to a complete split, calculates outlet flows, and tests component mass balances. By intentionally adding extra water to the washing stream, it creates a detectable imbalance, showing why accurate measurements and mass balance checks are essential in process simulations. Reactor balances. Reactor balances extend mixer and splitter balances by adding chemical reactions. Mixers and splitters do not change chemical identities, but reactors convert reactants into new products by rearranging atoms. Total mass is still conserved, while the amounts of individual chemical species can change, such as when ethylene and water form ethanol. The main idea is to separate overall mass conservation from component changes caused by reaction chemistry. Begin a reactor balance by identifying the inlet and outlet streams and the chemical species present. Because real reactors may include incomplete conversion, excess reactants, inert materials, side reactions, or recycling, the outlet composition can be more complex than the main reaction suggests. For example, methane combustion mainly produces carbon dioxide and water, while nitrogen remains mostly unchanged. But unburned methane or carbon monoxide may also appear. Key ideas for analyzing these systems are stoichiometry, conversion, selectivity, and yield. Reactor balances are based on conserving atoms. Every atom entering the reactor must appear somewhere in the outputs, whether in products, unreacted materials, byproducts, waste, or emissions. This helps check whether a proposed process is realistic, since a product cannot contain an element that was never supplied. These balances are essential for estimating raw material needs, product yields, and environmental outputs, linking chemical reactions to practical process design. Python code. Reactor balances. Represent reactor streams using dictionaries, apply stoichiometry and conversion with care, and verify mass closure to ensure the results are consistent. A dictionary is created to store molecular weights for selected chemical compounds. Each entry links a compound's formula to its molecular weight in kilograms per kilomole. This makes the values easy to reuse in later mass flow and balance calculations. The feed stream is represented by a dictionary of molar flow rates entering the reactor. It includes 100 kmols per hour of ethylene, 150 kmols per hour of water, and no ethanol initially. This defines the starting amounts of each component before the reaction begins. The ethylene conversion rate is set at 80%, meaning that this fraction of the feed ethylene reacts. The amount of ethylene consumed is found by multiplying the initial ethylene feed by 80%. The reactor outlet stream is found by applying the reaction stoichiometry to the feed. Ethylene and water are each reduced by the amount that reacts, since they are consumed in equal amounts, while ethanol is increased by that same amount. This gives an outlet composition that matches the chemical change in the reactor. To check the mass balance, calculate the total mass flow for both the feed and outlet streams by multiplying each component's molar flow rate by its molecular weight and adding the results. The difference between the outlet mass and the feed mass is the closure error. This value shows whether the mass flow calculations are consistent. The output introduces the reactor reaction where ethylene reacts with water to form ethanol. It then reports the ethylene conversion rate as a percentage and clarifies that the component flow rates are given in kmols per hour. The code compares each component's flow into and out of the reactor by reading values from the feed and outlet data. It then prints the component name with the inlet and outlet flow rates rounded to 1 decimal place. This gives a quick check of the component balances and helps confirm the reactor's stoichiometry and conversion. The code reports the total feed mass and outlet mass in kilograms per hour, giving a quick check of what enters and leaves the reactor. It then prints the closure error, which is the outlet mass minus the feed mass. This value shows how closely the mass balance is satisfied and helps flag any process discrepancy. Set a very small tolerance for the mass balance closure error, then compare it with the absolute closure error. If the error is within the tolerance, the mass balance is marked acceptable. Otherwise, it is flagged for data checking. The final status is printed to show whether the balance is consistent or needs further investigation. This script simulates a reactor where ethylene and water react to form ethanol, assuming 80% ethylene conversion. It uses stoichiometry to calculate outlet molar flows, converts them to mass flows, and compares total inlet and outlet mass to check the mass balance. The output reports the component flow rates, conversion, total mass flows, and whether the closure error is small enough for the balance to be considered consistent. Balance checks. Residual balance checks. A residual balance check tests whether a material balance is complete by comparing all inputs, outputs, and changes in the system. In a steady-state process with no reactions, material in should equal material out, so the residual should be 0. For reacting systems, it should be 0 only after accounting for material produced or consumed by reactions. This makes the residual a useful diagnostic for checking whether the data, assumptions, and process description are consistent. Residual balance checks are useful because they can be done at both total and component levels. A total mass check may show an overall discrepancy, but it may not reveal which material is responsible. Checking individual components, such as solids in wastewater treatment, helps identify hidden inconsistencies and ensures the balance is internally consistent rather than only roughly correct overall. A residual that is not near 0 signals that the data or model may be missing something important. It could reflect a missing stream, wrong flow rate, unaccounted reaction, changing inventory, evaporation loss, or measurement error. Use the residual as a clue to decide whether the discrepancy is small enough to accept or whether the data, assumptions, or process need further review. Python code, residual balance checks. Residual checks help identify unexplained material amounts, while component balances can reveal hidden inconsistencies. Using small tolerances helps distinguish normal noise from real problems. The inlet mass flow rates are organized in a dictionary with two feed streams. The first feed contains 80 kilograms per hour of water and 20 kilograms per hour of ethanol, while the second contains 10 kilograms per hour of water and 30 kilograms per hour of ethanol. This structure makes it easy to access and work with each component flow rate for the inlet streams. The outlet mass flows are stored in a dictionary for the product stream, with water flowing at 88 kilograms per hour and ethanol at 52 kilograms per hour. This information defines the component flows leaving the system and supports later checks of the mass balance residuals. A tolerance value of 1.0 sets the acceptable margin of error for checking residual balances. It helps separate small, ignorable differences from larger discrepancies that need investigation, so the mass balance can be judged against a clear limit. To prepare for mass balance calculations, collect the unique components from all inlet and outlet streams. This is done by combining the component names from each stream into one set, then sorting them into a consistent order. The resulting list provides a common basis for checking balances and identifying discrepancies. First, calculate the total mass flow of each component across all inlet streams. For each component, add its flow rates from every inlet, treating missing components as zero. These totals show how much of each component enters the system and provide the basis for a later balance check. To check the outlet side of a mass balance, we total the mass flow of each component across all outlet streams. For each component, we add its flow from every outlet stream, using 0 when that component is absent. These totals can then be compared with the inlet totals to identify any discrepancies. For each component, we calculate the residual by comparing the total amount entering the system with the total amount leaving it. These residuals show whether the material balance closes or if there are discrepancies that may indicate errors. The code adds the residuals from each component to find the total residual. This value shows the overall mismatch between inlet and outlet mass flows across the system, helping indicate whether the system is balanced or needs further investigation. The code prints a header to mark the start of the residual balance check in kilograms per hour. This tells the reader that the following diagnostic output is about checking the system's material flow balance. The code checks each component's residual against a tolerance using its absolute value. Components within the tolerance are marked as passing, while those outside it are flagged for checking. It then reports each component's name, rounded residual, and status, so imbalances can be identified quickly. The overall residual balance is checked by comparing its absolute value with the selected tolerance. If it is within that tolerance, the balance passes. If not, it is marked for further checking. This applies the same acceptance rule to the total material balance as to the individual components. The code prints a short summary of the total residual value. It shows the residual rounded to one decimal place and reports whether the overall mass balance passes or needs checking based on the set tolerance. This gives a quick indication of whether the system is within acceptable limits. The code finds the component with the largest imbalance by comparing the absolute residuals between inlet and outlet totals. Using absolute values means the largest discrepancy is identified, whether it is positive or negative. This highlights the component whose data may need the most further investigation. The code finds the component with the largest residual by comparing the absolute size of each discrepancy. It then recommends checking that component's data first, since it is the most likely source of the main issue. This script checks component mass balances by comparing the total amount of each component entering a system with the amount leaving it. It calculates residual differences, tests them against a tolerance, and reports which components pass or need further review. It also checks overall system closure and highlights the component with the largest discrepancy, helping identify possible material balance inconsistencies. Tolerance checks. Tolerance checks decide whether a material balance is close enough when measured inputs and outputs do not match exactly. Small differences are common because of rounding, estimated compositions, and limited calculation precision. By setting an acceptable range, tolerance checks prevent minor discrepancies from being treated as real process problems. What counts as acceptable depends on the process, since the same imbalance may be negligible in a large refinery, but important in a precise pharmaceutical operation. When setting a tolerance check, use both absolute and relative tolerance. Absolute tolerance works well for small quantities or limited measurement precision, while relative tolerance is better when stream sizes vary because it judges imbalance compared with the total amount. Apply the tolerance consistently to both total mass and individual components, since an overall balance can look acceptable even when specific components are estimated poorly. Choosing a tolerance requires engineering judgment based on data quality and the purpose of the calculation. Early design work can use wider tolerances, while reconciliation and quality checks need tighter ones. When a balance falls outside tolerance, it should prompt investigation rather than be treated as an automatic error, since causes may include missing data, conversion mistakes, or timing differences. In automated workflows, tolerance checks help flag problems early and support more reliable calculations. Python code. Tolerance checks. Tolerance checks judge residuals against realistic engineering limits, so small residuals may still mean the balance is acceptable. Checking individual components is also important because total balances can hide errors. This line tells the user that the script needs no extra packages. It runs using only Python's built-in features, so no additional setup or dependency management is required. Two tolerance values are used to judge whether expected and actual results are close enough. An absolute tolerance of 2 accepts any difference up to 2, while a relative tolerance of 0.005 allows small differences compared with the size of the values. Together, these tolerances make engineering checks fair for both small and large values. A dictionary is used to store inlet flow rates for the system in kilograms per hour. It records water at 1,000 and ethanol at 500, making each component's flow rate easy to access and use for later balance checks. The code records the outlet flow rates for water and ethanol leaving the system. Water is set to 998.5 kilograms per hour, and ethanol to 497 kilograms per hour. One value is intentionally rounded to create a small inconsistency for later tolerance testing. The check balance function evaluates whether a component's input and output flows are balanced. It finds the residual by comparing the input flow with the output flow, then normalizes that difference using a scale based on the larger flow magnitude, with a minimum scale of 1. This makes the discrepancy easier to judge against tolerance limits. The balance check sets an acceptable tolerance by using whichever is larger, the absolute tolerance or a relative tolerance scaled to the flow size. It then compares the residual's absolute value with that limit. If the residual is within the limit, the input and output flows are considered balanced within acceptable bounds. The function marks the balance check as pass if it meets the required condition, or fail if it does not meet the tolerance. It then returns the component name, residual value, tolerance limit, and final status as a compact summary of the result. The process creates an empty list to store balance check results, then checks each inlet component one at a time. For each component, the balance check function compares the inlet flow with the matching outlet flow, using 0 if the outlet value is missing. Each result, including the component, residual, limit, and status, is saved, so every component's balance is assessed and recorded. The code stores each component's balance check result in a single list. This collects whether each component's flow rates stay within the allowed tolerance, making it easier to review the results and identify any component that fails the balance criteria. The code sums the inlet flows to find the total material entering the system, then sums the outlet flows to find the total material leaving it. These two totals are compared to check whether the overall material balance stays within the allowed tolerance. The code checks the overall material balance by comparing total input and output flows against an acceptable discrepancy. Pause. It then combines this total check with the individual component checks into one result, making it easier to review all balance issues together. The output begins with a tolerance check results header, then prints a compact summary for each component and total balance check. For each item, it reports the name, residual, tolerance limit, and whether the check passed or failed. The values are formatted consistently so engineers can quickly interpret the balance results. The code finds which components failed the balance check by scanning the check results and collecting the names of any components marked as failed. This makes it clear which specific items did not meet the tolerance criteria. It also shows why looking only at the overall balance can hide important component-level problems. The code creates a final summary message for the balance tolerance checks. If any components failed, it tells the user to investigate those components by name. If none failed, it reports that all balances pass, then prints the message as the diagnostic conclusion. This script checks whether water and ethanol material balances are within acceptable tolerances. It compares each component's inlet and outlet difference against a limit based on absolute and relative tolerance, then also checks the overall total balance. The output reports whether each balance passes or fails, and flags any failed component for investigation. The key point is that a total balance can pass even when individual component balances fail, revealing hidden discrepancies. Missing data. Missing data can make a material balance check unreliable because the balance depends on knowing process inputs, outputs, and internal changes. If important values such as feed flow, product composition, or vapor loss are not measured or recorded, the balance may appear incorrect even when the process is operating normally. In these cases, the problem is often incomplete information rather than an actual process fault. When looking for missing data in a material balance, examine the process structure and the role of every stream, even small ones. Minor vents or wastewater streams may carry important components such as volatile material, unreacted feed, or dissolved products that affect balance closure. Also separate information that is truly missing from values that can be calculated. If too many key values are absent, the problem is underdetermined and may have more than one possible solution. Missing data must be handled carefully to avoid false conclusions about process performance. If a balance does not close, first confirm that all inputs and outputs are included before assuming leaks or unreported reactions. Clearly noting which values are measured, estimated, assumed, or unavailable helps show the reliability of the balance, communicate uncertainty, and decide whether more measurements are needed. Python code. Missing data. Missing data can make material balance problems harder to spot, especially in incomplete process streams. Simple checks can reveal these gaps, as illustrated with water evaporation data. The process begins by setting the known stream masses. The feed entering the system is 1,000 kilograms, and the concentrate output is 420 kilograms. The vapor mass is not yet known and will be estimated later. The process defines water mass fractions for 3 streams to support the water balance. The feed is 85% water, the concentrate is 40% water, and the vapor is entirely water. The stream data is organized into 2 dictionaries, one for inlet masses and one for outlet masses. The feed and concentrate masses are known, while the vapor mass is left unknown for now. This structure makes the stream information easy to access and use in later calculations. To handle missing outlet mass data, first identify the streams whose mass values are unavailable. Then collect the masses that are already known from the remaining outlet streams. These known values can be used later to estimate the missing vapor mass. The code first checks whether a direct total mass balance is possible by confirming that no outlet streams are missing. If all outlet masses are known, it sums the inlet masses to find the total entering the system, and sums the known outlet masses to find the total leaving. These totals can then be compared to check the balance. Estimate the missing vapor mass by subtracting the known mass leaving the system from the total mass entering it. Then record this estimated value with the outlet data so the mass balance includes the newly calculated vapor amount. To check the water balance, compare the water entering with the water leaving the system. The input is found from the feed mass and its water fraction, while the output comes from the water in the concentrate plus the vapor, assumed to be pure water. The difference between these amounts shows any imbalance and helps judge the vapor estimate and overall consistency. Set a tolerance of 1 kilogram to define the acceptable error in the water balance. Then compare the size of the water gap with this tolerance. If the gap is within that limit, the balance is considered closed and the estimate is reliable. The report identifies outlet streams with missing data, checks whether a total mass balance can be calculated from known outlet masses, and shows the estimated vapor loss. It then reports the water balance gap and tests whether that gap is within the allowed tolerance. The main point is that missing data should be estimated and checked before using the balance results to diagnose process faults. This script checks a water evaporation process for missing stream data and estimates the unknown vapor mass. It uses the known feed and concentrate masses, identifies the vapor stream as missing, and estimates it from the overall mass balance. It then tests whether the water balance closes within a chosen tolerance and reports the missing stream, estimated vapor loss, balance gap, and result. The key point is that missing data should be estimated before drawing conclusions about process problems. In this lecture, you learned to represent process streams and component flow rates in Python, compute material balances for mixers, splitters, and reactors, and check balance closure and identify inconsistent input data. In the next lecture, Lecture B, we will go over energy balances.
Thank you for your attention. See you all in the next lecture.